Alright, so in this tutorial we are going to introduce the concept of electric potential, or also known as voltage. Electric potential sounds like potential energy. They're close related, but they're not quite the same thing. So I'm going to tell you right off, be very, very careful. When we say just potential, that means voltage. If we want energy, we'll say potential energy. So let me kind of give you a context for that. So let's go back to something we're familiar with, parallel plates. So when I have parallel plates, we know we have an electric field between them. And what I want to convey to you is not only is there a force within a field, an intensity, there's energy stored in that field. And the reason there's energy stored in there is because these charges, Q on the plate and Q on the bottom plate, okay, in order to get them onto that plate, you just can't do that for free. You have to do work on them because those charges really don't want to be anywhere near each other. So as we put more and more positives on one plate or negatives on the other plate, you're doing work and work and work. And so you're storing energy within or between the two plates. Okay, so just like in a room where there is a gravitational field from the ceiling to the floor, there is energy potentially there by lifting something up from the floor to the ceiling. So if we decide to take a charge and put it in this field, okay, we can, it wants to go toward the top, but as it goes towards the top, there's going to be a gain in kinetic energy. So the stored energy can be used to move charges, test charges that is, across the field and convert to other forms, especially kinetic energy. Okay, so what we want to do with this, or any situation where you have a electric field, is that we want to quantify the amount of energy stored in that field, or the potential for there to be energy. Okay, and that, not potential energy, but the potential to have energy because of that force field. So we define something called energy per unit charge. If you remember the electric field intensity, E was defined as force per unit charge, and that was a way of quantifying the strength of the field based on the source. We want to do something very, very similar, but in terms of energy. Okay, and so energy per unit charge is called electric potential. Again, that's not the same. Oops, I should say electric potential. It's not the same as potential energy, even though they're very close related. And the more common name for this, is something you're more familiar with, is voltage. Okay, we've all heard about voltage, danger high voltage with various situations, voltage from a battery, etc. And that's actually a very, very important measurement in electricity. Okay, so while this concept right now is fairly abstract, it turns out to be very, very important when we want to understand something like a basic battery and bulb electric circuit. Okay, so the equation at the level we want to worry about is fairly simple. Okay, so voltage is given a symbol capital V, not lowercase v, and by definition, if we remember the words up there, it's work done on a system per unit charge that was moved in that system. Another way we can look at that is the change in energy in a system. I'm going to call it potential energy per unit charge. Okay, so that's what you find in your reference tables. However, we often use this equation for a different reason, not so much to find voltage, but to find the amount of energy that a charge gets by moving across a field. So if we rearrange this, we can say that the work done by a charge is equal to how much charge moves multiplied by the potential. Or we can say the change in potential energy of an object equals Q times the change in potential. So if we go back to our parallel plates up here, okay, in other words, when this electron, it experiences certain voltage at that point. We'll call that V1. When it's at the positive plate, it's at another voltage. We'll call it V2. So when it goes across this voltage, which is set because of the plates, it will gain energy. And we can calculate the gain in energy by how much charge the electron has multiplied by the change in potential. So potential is a convenient way of quantifying the potential to store energy. Okay, so we got to give units. Well, the units of voltage are work. If it's work divided by charge, that would be joules per coulomb. All right. So if we have a 5-volt source, for every coulomb of charge that moves across that 5 volts, we'll have 5 joules of energy. And the more common name is a volt, which also has the symbol capital V. Okay. And it's a scalar quantity, meaning it does not have direction associated with it, which turns out to make it even more friendly to use. So let's just use the rest of the time to do some examples, just kind of give you a feel what it is, and we'll continue to do this in class. All right, so let's take the parallel plates above. So let me just kind of redraw them over here. Here's the positive plate, here's the negative plate. All right, and you are told that the potential difference, so we got to make sure we understand vocabulary. Potential difference is just another way of saying the difference in voltage. Okay, between the positive and negative plate is 300 joules per coulomb. So I'm going to label that V. And an electron, so that's a key thing. So what do we associate with electron measurement-wise? We should associate that with a charge, that's Q, or potentially a mass, and it allowed to accelerate across the plates from the negative to positive. What is the change in potential energy? So in other words, if we put an electron here at the near the negative plate, it doesn't want to be there, it's going to zip across to the positive plate and gain kinetic energy and lose potential energy. Okay, so if you understand the terms and the variables, this is a very easy equation to solve. We got V, we have Q, I'm looking for an energy, so our equation is simply W, or change in potential energy, they're the same thing, equals Q times the voltage. So our Q, let's make sure we get that right, 1.6 times 10 to the negative 19th coulombs, multiplied by the voltage, 300 volts. All right, multiply that out, and we get 4.8 times 10 to the negative 17th. So it's a tiny value. We have volts times coulombs. You can leave it like that, but since it's energy, we know it has to be a joule. All right, so I'll leave it to you to convince yourself that a volt times a coulomb is a joule. So that's the loss in potential energy. Where did the potential energy go? Well, it went to kinetic energy. So we could ask yourself, how fast is the electron going? So it's a very convenient way of determining that rather than doing force and acceleration and then some kinematics. So from a conservation of energy standpoint, we can say that the loss in potential energy went to a gain in kinetic energy, and we know that kinetic energy is equivalent to 1/2 mv squared. Okay, so what do we know about the energy? It's going to be 4.8 times 10 to the negative 17 joules equals 1/2. The mass of an electron we can look up in the reference tables, 9.1 times 10 to the negative 31 kilograms times V squared. All right, so I do the manipulation, and if I solve for V, okay, even though we have a fairly, it's a high voltage, you'd be surprised how fast the electron's going. So it turns out this is about 1.0 times 10 to the 7th meters per second. That's a huge speed. That's a tenth the speed of light. So you don't need large voltages to get charges to move really quickly. Okay, now, what if we change? All right, now another question we can ask is, what if instead of 1 electron, we put 5 electrons at that location? All right, so I'm just going to put it here. It's still near the negative plate. What would change about the situation? Okay, first question, would the electric potential change? In other words, voltage. Okay, think about that for a second, because again, this is a very abstract concept. We want to understand what voltage depends on and what it does not depend on. Okay, so remember, voltage is due to the field charges that set up the field in the first place. We're not changing that by bringing in more electrons, because we're not changing the charges in the plates themselves. So the electric potential would still be 300 volts. Okay, it hasn't changed. However, since we brought more charge in there, 5 times the amount original, our potential energy is going to be 5 times greater. Okay, so if our original energy was 4.8 times 10 to the negative 17th, it's going to be roughly 24 times 10 to the negative 17th. So keep that in mind. It's kind of like electric field intensity. Electric field intensity depends on the field charges, not the test charges. It's similar with voltage. All right. Now, if you notice in the last problem, the amount of energy that the electron gained was really small amount. Okay, so physicists developed a new unit of energy for situations like that. And this is something you have to be familiar with. We're not going to do a ton with it, but I feel this is the time to introduce it, and we'll play around with it more. So just come in with questions if you're completely lost what I'm talking about. So the normal unit of energy is a joule, okay, and that's for everyday objects. But when we're dealing with really tiny particles, we want to come up with something that's more appropriate rather than keep saying 10 to the negative 18, 10 to the negative 19 joules, etc. So we call that an electron volt. A funny name, but the name kind of tells us what it does. So the electron volt is defined, and by the way, the symbol for electron volt is EV. Okay, it's the energy needed to move one electron across 1 volt of potential. Okay, 1 electron would be Q, 1 volt of potential would be V, so Q times V is energy, as we saw above. So the conversion factor is pretty straightforward, and it's in your reference tables. 1 electron volt of energy is 1.6 times 10 to the negative 19th joules. And there's that 1.6 times 10 to the negative 19th again. This is for an energy conversion. We've also seen it for a charge conversion. So in part C of above, what energy would 5 electrons acquire? Okay, so let's go back to the problem. We have a voltage of 300 volts across here. We're putting 5 E's, and they're going to accelerate across. And we said that the amount of energy they gain, I'm going to call that W now, is Q times V. Okay? Well, we could put in the number of coulombs this is, but when we're using the electron volt as our energy source, we can make it simpler. We can just say their Q is 5 E's, and it's going across 300 volts. So our energy is 1,500 electron volts. Boom. And if I ask you to calculate how many joules that is, then I would use my conversion factor. I would make a little table. Okay, and I see I have 1 electron volt per equals 1.6 times 10 to the negative 19. So I'm going to put 1 electron volt on the bottom, 1.6 times 10 to the negative 19th on the top, multiply them, and I will get 24 times 10 to the negative 17 joules, or 2.4 times 10 to the 16th. So it's a convenient way of doing energies when you have small charges. All right, let's do one last example, and then we'll do the rest in class. Suppose we took our static generator, and on a good day, we build up 200,000 volts. Yep, I'm not making it up. That's a true statement. So those static generators can create huge electric potentials. And you're probably thinking, holy crap, that's a lot of voltage. That's really, really dangerous. Yet we already know that it's not dangerous because we've touched them before, got shocks, and we've been no worse for the wear. Okay? So we want to make clear about something about what high voltage and why it can be dangerous, but not necessarily. So let's say we put 5 microcoulombs on a sphere. So how much energy is transferred to me when I touch it, okay? So if this is the static generator, right, and there are 5, forget about the negative right now, that's not really relevant. There's 5 microcoulombs on there, okay, and it touches me. They're going to transfer across a 200,000 volt potential. So the energy acquired by me, I'll just call it W, is nothing more than QV. And my Q is 5 times 10 to the negative 6 coulombs, not a whole lot, but certainly more than an electron, times 200,000 volts. And multiply that out, and I get a whopping 1.0 joules. Okay? So there's not a whole lot of energy, even though it's a very high voltage. So keep in mind that high voltage is only dangerous when a lot of charge is involved. We're talking coulombs and coulombs, and in a circuit, charge is measured more along the lines of something called current, but that's something we'll discuss later on. Okay, so we'll do the other examples in class to give you a better practice with that.